Assalamu alaikum student. Today lectures we will discuss some examples of representations of Lie groups. In our previous lecture we already discussed the definition of representation of Lie groups with its types, which are unitary representations, adjoint representation, dual representation and irreducible representation. But now today lecture we will discuss some examples of representation of Lie groups, right? So let's start. First of all, unitary representation of number. Unitary representation of real numbers. Let h is equal to L square r in comma dx for each a belong to R. Define Ta from h by this map, where here h is the square integrable functions, right? Then we find a map from h to h, right? By this Ta of f x is equal to f of x minus a, right? So we define the map in this way. First of all, we take h, this which is a square integrable functions, right? Clearly Ta is a unitary operator for each. It means that this operator Ta is a unitary operator for every real numbers, for each number a belong to R, right? Next, clearly Ta, this is a property of a unitary representation, where we can write in this way Ta into Tb. It means that when two map multiply to each other, then we can write in this way their subscript add to each other, right? Next we will move a map. A is a strong continuous. This map is a strong continuous, so T is a unitary representation of R. So this map is T is a unitary representation of R. This representation is not a reducible representation, right? It means that this unitary representation is not a reducible representation, right? The theory of Fourier transformation allow one to determine all closed invariant subspaces of H. It means that the theory of the Fourier transformation determine the all invariant subspace of H, right? It means that with the help of Fourier transformation we can calculate all the invariant subspaces of H. H where? Yes, square integrable function, right? So this is a unitary representation of real numbers. Now we move to representation is a unitary representation of a Heisenberg group, right? Consider the Heisenberg groups, right? And here is the elements in 3 by 3 matrices where A, B, C belong to R, right? Now we consider the element H, where H is a non-zero element. Find a unitary operator. We define a unitary operator H capital pi H bar on L2. L2 we already discussed in previous examples, where we can say that this space is a square integrable space, right? Then by defining by this map, right? And this map is capital pi H, and where is a matrix this, right? 3 by 3 matrix, and F and e की power minus iota hb and dot e की power iota hcx into f of x minus a, and this equation number is 1. It is clear that right hand side of this equation 1 has the same norm as f, so pi h is the unitary, right? So this is a unitary representation of Heisenberg groups. Here we take first of all the Heisenberg groups, which is a 3 by 3 matrices. Then we define a map, and here is map is in this way, right? So the norm of this right hand side of this equation number 1 is the same as, and that's why we can say that this map pi of H is a unitary representation of Heisenberg groups, right? Now we see next map capital pi H into A tilde, B tilde, 0 1, C tilde, 0 0 1, and other elements by H of A 1, A 0 1, C 0 0 1, right? It means that we take the true element from 3 by 3 matrices from Heisenberg groups and apply the map by capital pi H, right, of into F. So when we apply this map, we will get this where e power minus iota h b tilde e power iota h c x c tilde x e power iota c h x h c into x minus a tilde f of x minus a tilde into a tilde, right? And further, if we simplify this equation, then we will get this expression e power minus iota into h into b tilde plus b plus c a tilde into e iota e power iota h bar into c tilde plus c into x, right? And here map f of x minus into a tilde plus a, right? So this show that the map a from a to pi of a is a homomorphism of Heisenberg groups into the U of L2 of R. This map is strongly continuous, so this is a unitary representation, right? This is so this pi h is the unitary representation of h, right? So this is a unitary representation of Heisenberg groups. Here we compute this map. First of all, we take the group of Heisenberg groups, then we take two elements, right? Then we apply the map on these elements, and these elements from the Heisenberg groups. After applying and simplification, we will get the map, and this map is strongly continuous. If the map is strongly continuous, then we can say that this map is a unitary representation of Heisenberg groups, right? So this is a unitary representation in capital pi h is a unitary representation of h, right? So this is a representation of Heisenberg groups, unitary representation of Heisenberg groups. Now we see next, compute all of the finite dimensional irreducible complex representation of Lie algebra small su2 special unitary 2 by 2 matrices, right? This is important because su2 is isomorphic to so3 special orthogonal 3 by 3 matrices, right? And because this so3 and su2 is it means that these two groups are mostly used in the quantum mechanics for the purpose of angular momentums, right? So now every finite dimensional complex representation small pi of su2 extend to the complex linear representations of complexification of su2, namely sl2 over c. It means that every finite dimensional complex representation may be extended to the complex linear representation of sl2 over c, right? The extension of small pi to sl2 over c is irreducible if and only if the original representation is irreducible. It means that the extension of sl2 is irreducible if and only if the original representation is irreducible, right? So now we see next, we see that studying the irreducible representations of su2 is equivalent to study the irreducible representations of sl2 over c, right? It means that after studying the representations of su2, we will easily find the representations of irreducible representation of sl2 over c, right? So next, let the basis, here we take the basis elements of sl2 over c, right? We have three basis elements, right? H, x and y, right? So computation relations of this basis here, x comma h comma x is equal to 2h, and h comma y is equal to minus 2y, and x comma y is equal to h, right? If next, if V is finite dimensional complex vector space, if V is a finite dimensional complex representation, and A, B and C are operator on V, right? A, B, C are operator on V, satisfy the AB is equal to 2B, right? And computation relation of AC is equal to minus 2C, and computation relation BC, B comma C is equal to A, right? It means that here we take the three basis element of SL to our C set of complex, and here is the computation relation of this, right? Then we take a finite dimensional complex vector space and three operators defined ABC. We define the three operators such that these computation relation are satisfied, right? Here is 2b minus 2c and a, right? You can see that their computational relationship are same because of the skew symmetry and by linearity of the bracket. The linear map small pi SL to our C to GL over V satisfying this relation pi small pi of h is equal to a, small pi of x is equal to b, and small pi of y is equal to c will be representation of SL to our C, right? So this is a representation of SL to our C, right? So this is our today lecture. In this lecture we discuss some examples of representation which have unitary representations of real numbers. Then we SU2, Lie algebra SU2, right? So this is our today lecture. If you have any question, you can ask in comments. In our next lecture, we will discuss some more example of representation of Lie groups. So thank you very much for watching this video.